Hi everyone, this is Abhinav and today we'll be discussing the 29th problem from the CP-31 sheet by TLE Eliminators under the 1500 rated problems. Let's begin. We'll move on to our CP-31 sheet. The 1500 rating mark is checked. Let's go on to the 29th problem, which is pride. Let's read the problem statement. You have an array A with length n. You can perform operations. Each operation is like this. Choose two adjacent elements from A, say x and y, and replace one of them with GCD of x comma y, where GCD denotes the greatest common divisor. Okay, so what is the minimum number of operations you need to make all of the elements equal to 1? So this is the question basically, that you are given an array and the only type of operations you can perform is just pick any two adjacent elements and replace one of them with their GCD. By performing these operations, what you need to do is you need to find the minimum number of operations you need to make all the elements equal to 1. So you have to basically make all elements equal to 1 and return the minimum number of operations required for it. For example, if you take the first test case, okay, so basically you will be given an n and an array of size n. So here if you see this first test case, what we can do is we can perform an operation like pick any two adjacent elements and then replace one of them with their GCD. So let's suppose we pick 4 and 6. So if we pick 4 and 6, GCD of 4 and 6 would be 2. So we can replace any one of them with 2. Let's say we replace this one with 2. Okay, then what we can do, we can again pick any two of them. Let's say we pick these two. Okay, so if we pick these two, their GCD would be GCD of 3 and 2 would be 1. Okay, so we can replace either of them with 1. Let's say we replace this one with 1. Okay, then maybe we can pick these two. Once we have got a 1, what we can do is if we pick any element, GCD with 1 would remain 1 only. So we can pick these two, replace this with a 1. Okay, so if we pick these two, replace this with a 1, then we can pick these two and replace this with a 1. Okay, and now here we have got 1 and 2. So we can pick these two and replace this with a 1, and then we can pick these two and replace this with a 1. How many operations did we need in total? Like if we did like this was the first operation we did, this was the second we did, and then third, fourth, and this was like fifth operation, and this was sixth operation. I think 6 operations we did. Okay, whatever. So this is like one way how you can convert all of the numbers to 1. Now you need to find that how you would perform the operations optimally so that this can be achieved in minimum number of operations. Okay, so here we required 6 operations, the first way that I showed you. Can we do it in lesser? Let's say I do it like this. I pick these two elements, their GCD would be 1. So let's say I replace this with a 1. That's one operation. Okay, then let's say I pick these two elements, replace this with a 1. That's another plus 1 operation. Okay, then we can pick these two and replace this with a 1, plus 1 operation. Pick these two, replace this with a 1, plus 1 operation. Pick these two, replace this with a 1, plus 1. So here we can see we required only 5 operations and we were able to achieve this. So for this, actually you can see the output was 5. So the minimum number of operations was 5. At least 5 operations would be required to convert this array into an array having all ones. So this is the answer that you need to return. Okay, so I hope the problem statement would be clear. Now let's try to find some solution for that. So before looking at the solution, let's look at the constraints of the problem. So n is given up till 2000. So if you look at the constraints, n is given up till 2000 and the values of ai can vary up till 1 in 9. 10 to the power 9. Okay, so looking at these constraints, what can you say about how optimized the solution should look like? What should be the complexity of the solution? You can see that n is up till 2000. So if you do something like even order of n, that would be completely fine. If you do something like order of n square, even that requires 4 into 10 to the power 6 operations only. The square of this would be this much. So this is also absolutely fine. You can do 10 to the power 8 operations in 1 second. If you go to something like n cube would require like 8 into 10 to the power 9 operations. This would not be accepted. This would give us a TLE. So this is not allowed. But anything up till n square were fine. These were fine, these were fine. If you even go to something like n square and add some extra log n type complexities, that would also not add. This log n won't be too much. Maybe log of not n, if log of ai is also there, that may go up till 30 only. So this multiplied by 30 would also be almost fine till 1e8 only. So something like n square log ai I should write, log ai or log n, those complexities would also be fine. Okay, so these we can say are our expected time complexities in which we are required to solve the problem. We cannot go to something like order of ai. Okay, that would be 1 in 9. So you have to do in some quadratic order of n, and some extra log factors can be added. That doesn't affect our answer. So this is our expected time complexity. Once we know in what order we need our solution should look like, then we can think about an approach to find such a solution. Okay, now what approach can we think about? So let's look at the operations deeply. So you have an array, and in that array you have some numbers. Okay, then what you need to do is you need to convert all these numbers to 1 using the operation that select any two numbers, replace any one with their GCD. Okay, let's say there are two numbers x and y, so they would be replaced by the GCD of x comma y. Okay, so if you look, when do we get a 1? Okay, what we want to achieve is we want to achieve a 1 for every element. Okay, so one case is initially only the complete array is all ones, then we won't require any operation, the answer would be 0 directly. But apart from that, if there are any non-1 present in the sequence, then we would have to replace that with a 1. How do you replace a number? The only way to replace a number is by the GCD of that number with one of an adjacent number. So whenever you take the GCD of two numbers, this would always be less than both the numbers, less than equal to both the numbers. So taking GCD of more and more numbers is always going to reduce my number. Okay, and after some point it may become 1 also. So if x and y are not co-prime, if x and y are co-prime, then their GCD would be 1. That's when we get a 1. So the only way we can get 1 for a GCD is if x and y are co-prime, they don't have any common factors. And once we get any single one, okay, let's say this whole array doesn't contain any one, and you maybe do a GCD of two adjacent element and you get a 1. So what can you do? If you get a 1 on any one element, if at least one element, then as you can see in this example, what we did this GCD, replace one of them with a 1. Once we got a 1, we just used that one to spread this to the whole array, because if you get a 1 at any point, you can do a operation like this, make this element 1, operation like this, make it 1, operation like this, make it 1, do an operation like this, make it 1, operation like this, make it 1 1 1. This way you can just, if you even get a single one, you can make all the numbers 1 by doing an operation like this. But is this the minimum number of operations required for this case? How can you prove that? Because you may think that there may be some other ways through which we, in less number of operations only, we can get all ones. Okay, now the thing is, in one operation you can only replace any one number. So if you are replacing only one number, so if you are replacing only one number in one operation, that means if there are n numbers, all of them are not 1. Okay, so if you have n numbers, all are not equal to 1, then in order to make all the numbers n, you would have to do at least one operation for each number. In one operation you can replace any one number only. You can only make a change to the array at any one index. So in order to make n numbers all equal to 1, if they are unequal, you would require at least n operations, that you can like understand that at in any case, whatever type of operation you do, you would require at least n operations to make all the numbers 1, that you can prove. And if you can do it in n operations only, that would be your minimum answer. So here in this case, what we can see, we take these two adjacent elements, their GCD was 1, so we replace one of them with 1, that required one operation. Then this is 1 2 3 operations, 4 5 6 7 8 9 10 operations. So if there were 10 numbers in 10 operations, we were able to do. So for this case, like by proof, we can say that n would only be the minimum number of operations required. We can never go to less than n if all the numbers are not 1. Okay, so for this case, so for the case where any two adjacent numbers give a GCD of 1, we can say, okay, so for the case where all numbers are not equal to 1 and any two adjacent numbers give GCD equal to 1. For this case, we can say our answer would be n, definitely. Now, what apart from this, what other cases we need to handle? First thing is, another case we can easily handle is when there is some 1 already present in the array. So if let's say there is a number which is already 1 already present, a 1 is already present in the array, what we can do, we can use this 1 to convert all the remaining numbers to 1. So if there is, this is 1 and these are all not equal to 1, let's say, then how many operations would be required? 1 operation, 2 operation, 3 operations. So apart from this number, for all the numbers, 1 operations would be required to convert them to 1. If there are, let's say, 2 ones already present in the array, then apart from these two indexes, for this, all the rest of the indexes would require 1 operation to convert them to 1. So we can say if there are x ones already present, if there are x ones already present, then my answer would be n minus x simply. Okay, so these two base cases you can say is done, this case and this case. If there are x number of ones already present, my answer is going to be n minus x. And if for the case where all numbers are not equal to 1 and there are any two adjacent numbers through which in one operation only we can get a 1, then my answer would be n. Now let's look at a case where even if you check for all the two adjacent elements, none of the adjacent elements give you a GCD of 1. Then how can you solve the problem? Okay, so for the remaining case where you have this array A, okay, and you checked that even adjacent elements are not giving you a GCD of 1, like you can look at maybe this test case only given in the problem. So here if you see, GCD of these two numbers was 2, GCD of these two numbers was 3. So any adjacent elements in one operations you could never get a 1. But we can do this if we'll take like this. GCD of these two would be 2. Let's say you replace this 6 with 2. Then GCD of this 2 and 3, that would be 1. So that way you can replace this with a 1 and then operation on this, replace it with a 1, replace it with a 1. So that way we required one operation here, one operation between these two, second, then this was the third operation, this was the fourth operation. So we required a total of 4 operations. Here the minimum number of operations was 4. So the number of operations was actually more than n. We were not able to do it in just n operations. Okay, so for these cases, how can you compute what would be the minimum number of operations? For that, if you look at how the operations are working, whenever you do, let's say this is A1, A2, A3, A4, A5, A6, A7, A8. Likewise, you have an array. So whenever you perform an operation, you would perform in any two adjacent elements. So if you perform in any two of the adjacent elements and replace any one of them with the GCD of those two elements, okay, what happens on consequent operations? So if you replace this one with its GCD and then you take a perform an operation with these two elements, basically what you are doing is you are doing GCD of A3 with the GCD of A4 comma A5, which is effectively GCD of A3, A4, A5. Okay, as you know about the property of GCD, you can basically combine them up. So if you are saying that you are taking GCD of A3 with the GCD of A4 comma A5, that's actually the GCD of all the three numbers. And same way, if you take perform an operation here after that, then you are basically taking GCD of A2 with the GCD of A3, A4, A5. So that would become GCD of A2, A3, A4, A5. So what you basically did is you got the GCD of these GCD of numbers in one particular range. And to do that, how many operations were required? One operation here, two operation here, three operation here. So in total, in three operations, you were able to combine four consecutive numbers and get their GCD. And this GCD can be replaced with any, would be replaced with the final GCD there. So either A2 or A3, one of them would get replaced by this GCD. Not all of them would be replaced by them. So after three operations, you can say that you can get a GCD from L to R after how many operations? Whatever is the difference, GCD from 2 to 5 you got in 5 minus 2 equal to 3 operations. Okay, whatever was the size of range minus 1. Size of range is R minus L plus 1, minus 1 is R minus L. To get GCD of 4 consecutive numbers, you require only 3 operations. So after R minus L operations, you get, so after R minus L operations, you can get a GCD from L to R. Now, can you do it in less number of operations? That's the first thing if we want to prove. So there may be other ways to get the GCD from A2, A3, A4, A5. Another way could be you select these two, get the GCD of A4, A5, maybe replace it here. You can select these two and get the GCD of A2 and A3, replace it here maybe. And then if you do the GCD of these two, basically you are doing the GCD of these two numbers, that would finally give you a GCD of A2, A3, A4, A5. But still, how many operations did you require? 1, 2, and then 3 operations to combine them. So you can like prove this also, that if you want to get GCD of 4 numbers, in every operation we can only combine any 2 numbers. So initially all of them are single, single, single. In one operation you can combine these two numbers to get their GCD. In next operation maybe these two can be combined to get their GCD. But if you want to combine all the 4, then you can imagine it like these are connected by these three, you can say these 3 connections. So whenever you take GCD of these two, you are breaking this connection. GCD of these two, you are breaking this connection. GCD of these two, you are breaking this connection. Or another way, GCD of these two, you break this connection. GCD of these two, you break this connection. GCD of these two, you break this connection. Finally, you would have to break all these 3 connections in order to get the GCD of this whole ring. So this way, like intuitively, you can get an idea that to get the GCD of a range of size x, you would require at least x minus 1 operations to get the GCD of a range of size x. Okay, so this is the minimum number of operations required for this. Once you know that, and the second thing you can prove is always like whatever kind of operations you do, you can only get GCD of a range from L to R only in this. You cannot get GCD of A2, A3 and A5 and skip A4. You can never get this because only way you can do the operations is through adjacent elements. So if you want to combine the GCDs of A3 and A5, you would have to combine A4 as well. You cannot skip it. So either you would do these two GCD and then these two, or something like this. You cannot do GCD of these two because only adjacent operations are required. So always whatever GCD you get, whatever you get in this array would be something like, they all would be either individual elements, which you can say the GCD of the same L2, GCD of the range from same to L to L. If I say, if I want to represent AI, that I can say is the GCD of a range from I to I only, just GCD of this one number. So basically all the numbers that you have in the array are actually GCD of a range of consecutive elements. So what you need to finally get is a 1. So how can you get a 1 in minimum number of operations is if you can somehow find what is the minimum size of a range that gives a GCD 1. If you can somehow find such a range of minimum size giving a GCD 1, then you can like finally calculate your answer. If you are saying that these four numbers combined give you a GCD of 1 and there is no other way to get a GCD of 1 in less than there is no other range of size less than 4 which gives a GCD of 1 in this array, then at least at least these three operations would be required to get a single one. And once you have got a single one, so you say after three operations you got a single one. Once you have got a single one, then you can just one by one convert all the numbers to one in how many operations you have already got one, and then there would be n minus 1 numbers left, so n minus 1 more operations would be required. So basically in 3 plus n minus 1 operations you can convert this whole array to all ones. So what we can say is, for the rest of the part, you can say the else of this. So if like this case can also be proved through the this concept only, that if there are any two adjacent elements that give a GCD of 1, okay, so that means you have got a range of size 2. That means you would require 2 minus 1 operation to convert to get a 1. So for this case you can say that one operation would be required to get a 1 because you have a range of size 2 which gives a GCD of 1 plus n minus 1 operations which gives actually n operations. So the remaining case that you solved also solves this case as well. So you don't need to specifically write code for this case. Your general case would also consider this as well. So what general case I'm telling is, what you need to do is find minimum size of a range that gives find the minimum size of a range that gives a GCD is equal to 1. Okay, so the minimum size of such a range for which the GCD of 1, if let's say that is okay, so if you can find that minimum size, then you can say your answer would be, that size would be whatever range you found for which the size is minimum, that size would be r minus l, would be the number of size would be r minus l plus 1, and the number of operations required would be r minus l plus n minus 1 operations to convert the rest of the n minus 1 numbers to 1. So this would be your answer for a very general case. Now, one more small case that you need to consider. What if there is no range that gives a GCD of 1? That means even if you take the GCD of this complete array, even if the GCD of this complete array is not equal to 1, that means there is a factor which comes in all the numbers. So you can never get a 1 in this array. For that case, you would have to print a minus 1. Okay, as it's written in the problem that print minus 1 if it is impossible to turn all numbers to 1. So it would be impossible to turn all numbers to 1 only if the GCD of this whole array is not equal to 1. If the GCD of the whole array is equal to 1, then there is somehow one way to convert it into 1. But if this GCD of this whole array is not equal to 1, that means you can never convert, you would return minus 1. So that you can consider as a base case only, that if GCD of the whole range of numbers, GCD of the whole array, if this is not equal to 1, then you can say your answer would be minus 1. Okay. So this is it. Now, how do you calculate this minimum size of a range that gives a GCD from L to R equal to 1? Now, allowed time complexity is up till n square. So I hope you can calculate in n square complexity to get the minimum size of a range which gives a GCD equal to 1. How to do that? Like, you can just brute force for every L. Okay, so you can fix your L. So in the array, so one by one, you fix this number as your L, then you would fix the second index as your L. One by one, you fix your L. Once your L is fixed, then start with this number, take the GCD with the next number, take the GCD with the next number until the minimum R required so that you get a GCD of 1. Okay, so for every L, one by one, you can take the GCDs until you get the GCD equal to 1. Once you have got the GCD equal to 1, you can stop at that R. That would be your minimum R for this particular L. And then same way again do a brute force starting from the next L. Okay, for this range you get the size of the range equal to R minus L. Okay, for some other L, if that size is smaller, you can minimize that in a separate variable, maintain the minimum size of the range. So that way brute forcing through all the L would be order of n, the n number of different L that can exist. Inside that, in order to find the R, you take GCD, GCD, GCD. At max, you would go to order of n, n GCDs you would have to do, and for every GCD, it would require a log factor as well. So n log of AI, you can say, would be the time complexity for a fixed L to find the minimum R, and overall time complexity would be n into n log AI. So n in n square log AI time complexity, you can calculate your answer, which would be absolutely fine for the given constraints. Okay, so I hope the logic algorithm is clear to you. We can quickly move on to our code. Okay, so here you can see in the main function I have taken the input part, so n and an array of size n. This is for the input part. Okay, once input is done, then I start with what all cases do we need to consider. The first case that we need to consider is this: if there is a 1 already present in the array, then we can just simply print our answer as n minus the count of ones that are present. So first let's count. Okay, we'll iterate through the whole array A, and if the value of any element is equal to 1, we do count plus plus. So in our count variable, we get the count of number of ones that we already have in the array. And so if that count was positive, then our answer would be n minus count simply, and we can return out. That's done. So this base case is covered here, that if the count is greater than equal to 1, then answer is n minus x. Okay, that base case is covered. Then another base case was for minus 1. Okay, if the GCD of this whole array is not equal to 1, then we print minus 1. So in a variable G, we maintain the GCD of the whole array. Okay, if we are iterating through every element, and we do the GCD for all the elements, and if that GCD is greater than 1, then we print minus 1 and return. Our case is done. Okay, once these two base cases are handled, then we what we need to do is, if none of the base cases are satisfied, we haven't returned out yet, that means there the whole range, the GCD of the whole range is equal to 1. So the GCD of the whole range is equal to 1. That means there exists some range of some size which gives a GCD 1, and it's also not the case that any of the elements is 1. So this would be the case used. So let's find the minimum size of a range that gives GCD L to R equal to 1. So we'll do the brute force technique. We'll initialize our answer with some value which is greater than all the values present. So at max, you would take the GCD, the range would be from the whole from 1 to n. So if that is the range, that would be n minus 1 plus n minus 1. So at max 2n minus 2 would be the maximum answer that you can get. So we take some upper bound only 2n, or you can also initialize it with some very big value of infinity, 1e9, etc. Okay, now we would calculate whenever we get some valid answer, we'll minimize this answer. Okay, we start with I equal to 1 to n. So this I is actually our L, okay, through which we are brute forcing. We are brute forcing for every L. Okay, so this is our L, and then for a fixed L, we start with initial GCD is for AI. and we iterate our j from I plus 1 up till n, and we take the GCD consecutively with aj. Whenever our GCD reaches 1, okay, we say this j is actually r, this is l. Okay, so if our GCD reaches 1, that means for this particular l to r, this particular I to j is the range which gives a GCD of 1. So our answer would be n minus 1 plus r minus l or j minus I. Okay, this was our answer, r minus l plus n minus 1. So n minus 1 plus j minus I is r minus l. So we'll minimize our answer. This is one possible answer for this particular j and I. So we go through all valid j and I and minimize our answer. Okay, and once we have got a GCD of 1, we don't need to go further and take more GCDs. It would remain 1 only. So we can break out from the inner loop. Okay, then in the outer loop again we'll start with a fresh L and do the brute force again. Okay, so this way we get our final optimal answer. Okay, so I hope the logic and code is clear. If you look at the time complexity, then this input part would take order of n time to take the input of the whole array. Here you are iterating through the whole array and taking GCD also. So this GCD would take log of AI time. So this whole operation would take n log of AI time. Okay, and this is of one operations. Here again you are iterating this n times inside also. At max you are going n times and you are taking GCD also. Okay, so this GCD would take log of AI time, and this is order of n. So overall n into n log of AI, you can say, is the time complexity for this. Okay, so you can say your overall time complexity in the worst case would be order of n square into log of AI. This you can say is your overall time complexity, which is almost optimal for the given constraints. Okay, space complexity, if you look, then you are just using an array of size n, and then these GCDs are all single variables, count single variable. So only thing you are using is an input array of size n, so that would take an order of n space. Okay, so I hope the space and time complexities are also clear. So this problem was basically about understanding GCDs and number theory. If you solve more such problems, you will get the intuition of where you can use GCDs and how you can use the properties of GCD to solve problems. So it was a nice problem of number theory. I hope you enjoyed the solution. Thank you so much for tuning in.